The Hubble telescope is reported to have cost $2.4 billion to put up. The Hubble telescope, Canada's contribution, apparently is going to go up for about $7 million. Jaymie Matthews is a professor of physics and astronomy at the University of British Columbia, and he's going to come and tell us about this next piece of Canadian ingenuity in space.
I'm wearing this after last night's party, and I introduced myself to several people as astronomers. I had many invitations to read palms and to cast horoscopes, so I thought I would come appropriately. It was a great party, by the way. IdeaCity, I've learned in only one day, is about connections, unexpected connections, connections that pass through Canada as a common nexus. It's also about expectations, meeting them, surpassing them, defying them, blowing up sacred cows. And what I'd like to talk about today are some of the unexpected connections in a pure esoteric science like astronomy and astrophysics that might relate to your lives, whether commercially, spiritually, artistically. And as an astronomer, one expectation that you have of me is that I'm supposed to show you pretty pictures of the cosmos. So I'll live up to that. If we'll put on the screen the first, here we go. This is a picture. We'll come back to something like this in a moment, but let me just say for the moment that you're looking at our past and possibly the future of some unknown civilization. As an astrophysicist, the expectation is that I'm going to be fairly boring and stuffy and that I'm going to bombard you with equations, and I don't want to disappoint you. So I do have an equation. I was going to put it up on the screen, but the computer, sort of our own little HAL 9000 over here, balked at showing this equation, so I'm going to have to show it to you in a different way. The equation, I'm going to do a little bit of a striptease here with all apologies to Hoffman. I've got the equation on my t-shirt, which I got in Spain, in Granada, at a very funky, very trendy shop. I don't know if you can see this, if this is up on the big screen. There we go. And it's lots of gobbledygook, even if you can't read it, which contains symbols like capital U and T and div of U, F of X. And essentially, it's describing the change of heat energy with time. And it's a real physical equation, which applies in a lot of situations. So what the heck is it doing on a t-shirt in a trendy boutique in Granada, Spain? And underneath, it shows that the people who put it on the shirt actually understood something of it, because the phrase says, "Are you getting hotter yet?" Now, I was at a meeting for solar variability and the effects on planetary environments and climate change. And so, of course, I wore this t-shirt, and you know, to climate change people, it's hilarious. That's what passes for humor in the climate change world. When I wore this shirt at the discotheque that night and met a flamenco dancer, she interpreted it in a different way. I'm not going to make that connection, and I didn't, by the way, because my lovely girlfriend Carol is sitting right there. But what's interesting is that somebody in the business of producing clothing to sell to sort of an elite audience decided to put on a physics equation that had to do with the change of heat energy. And was it an unemployed astrophysicist who was working for the company, or an enlightened CEO? I don't really know what that connection was, but it was a surprising connection, and they exist everywhere. But while I'm on this theme of heat change and climate change from the t-shirt, we can look at the next slide. Basically, here is the heat engine for the Earth. It supplies the heat and light that allows life to exist on our planet. And we know it changes. And astronomers are trying to study it and other stars in order to understand how it changes and how it affects our lives and our climate. Now, it changes on many timescales, and one of the timescales that astronomers are very familiar with is timescales of billions of years. As Carl Sagan would have said, billions and billions of years. You might wonder how an astronomer who is lucky to last for 100 years knows that things have been around and will be around for billions of years, and I'd be happy to try to explain that to you over the coffee break. I won't get into it now. But suffice it to say that the sun, you're seeing here, is a giant nuclear furnace. it's converting hydrogen gas, the most abundant element in the universe, into helium, the next most abundant, and it's producing energy, and the amount of energy it's producing is given by Einstein's equation that we heard yesterday, sort of from his disembodied brain, or his disembodied brain's keeper, the E equal mc squared equation. So that's what makes the sun shine. It's got like a nuclear clock ticking through its life, and we believe that the sun has a limited life. We know that there are other stars whose clocks are ticking at different rates. And in fact, I like to think of stars as cars, as automobiles. And if we can see the next slide, here's my example. Here's a star, another star in our solar neighborhood, in our neck of the woods, called Spica. You can see it with the naked eye easily on a warm, clear night. And this star is about 20,000 times brighter than the sun, but it's incredibly distant, so it just looks like a twinkle in your eye when you see it at night. But it's going to last for only, I say only, 10 million years, which is a very short lifetime for a star. And so stars like this are kind of like the sports cars of the universe. They're flashy, but they're not very fuel efficient. And in deference to our sponsor, I'm sorry, I didn't. Now, at the other end of the scale, there are the red dwarf stars. Very faint. Here's Wolf 359. For those of you who will admit in public to being Star Trek fans, this is where the Borg attacked the humans. This thing shines about 1/10,000th of the luminosity of our sun. It's a really feeble thing, but it'll last forever almost. It's certainly longer than the current estimated age of the universe, for at least 1 trillion years. And it's the equivalent of the Honda Civic of the universe. It's dull, but it's really fuel efficient. It goes a long way on its tank of hydrogen. The sun falls somewhere in between. It's kind of a mid-sized car, like the Aries that we saw in the video the other day. And we expect it has a total lifetime of about 10 billion years. Now, the project I'm going to talk about is going to use these principles to determine the ages of stars other than the sun for the first time, and even set a limit on the age of the universe. But the reason why I brought this up now is because we know that the sun is getting hotter very slowly as it evolves through its life. It's right now in middle age. It's nice and complacent. Like many human middle ages, it's quite boring, and we should be happy for that, because if it was doing exciting, rebellious things like blowing up, we wouldn't be here. But eventually, the sun is going to get large enough and bright enough that the temperature on the Earth is going to rise in probably 500 million years to a rather uncomfortable 50 or 60 Celsius as a global average, and eventually to above 100 Celsius, where the oceans will boil away. Now, this doesn't mean that the sun can be blamed for the current observations of global warming. In fact, most of the evidence that we're seeing now is that, in fact, human beings are competing with the sun. The sun is a factor, but humans are a noticeable factor and probably the dominant factor. And so this is another connection. By understanding the stars, we better understand our sun, and we better know how to cope with it, whether the sun is the culprit for global warming and whether we have to clean up our own act. And this brings me to the reason I'm really up here, is to describe briefly the MOST project. Now, MOST, here's our logo. The alphabet soup of letters you see below there just tell you that this is a unique combination of government through the Canadian Space Agency and even funding from the Ontario provincial government, universities, University of British Columbia, University of Toronto primarily, and Canadian industry, aerospace companies and so on, like Dynacon Enterprises, based here in Toronto as well. And MOST, if we see in the next slide, we promote as Canada's first space telescope. And if you want to leave now, just write down the website, and then you can learn all you want to know about it. Now, when you think about a space telescope, we've been making comparisons with the Americans through this meeting, and this is the space telescope that everyone thinks of. Let's just put things in perspective. This is our space telescope. And that's why we call it the Hubble Space Telescope. It's truly a Canadian project. The whole thing is the size. The whole thing is the size and mass of a suitcase. You could check it on an airplane and they would lose it for you. This happened to me. I lost my luggage twice due to an airline that shall remain nameless, but I was in Spain. Hint, hint. Hidden inside this bus, which we call a Vespa because it's so small, is the telescope itself, peeking out through a little periscope, almost like a child's toy, it seems. But it's a child's toy, which is about $9 or $10 million Canadian in total price, which at current exchange rates this morning was something like $27.95 US, I think. Actually, the figure that Dr. Znaimer used earlier was probably the American cost. It's probably about $6 or $7 million US. But that's incredibly cheap for an entire space mission with these kinds of goals. We kind of think of ourselves as the Zellers of space telescopes. And the telescope's actually been built and is undergoing testing, even as I speak, in Toronto, in a lab in northern Toronto, Spectral Applied Research. And a couple of views of it. It really is a thing of beauty, at least to those of us who have spent several years of our lives trying to make it to fruition, although it is quite tiny. Many of you probably own bigger telescopes. I think some of the telephoto lenses in the audience are larger than our telescope. It's small, but it's powerful, and it's capable of doing certain things that even the Hubble Space Telescope, that no other telescope on Earth or in space is capable of doing. And so it really will be an achievement, and that sounds non-Canadian to say, it sounds non-humble to say, but it really will be. One of the things we hope to do is look at stars like the sun and learn the sun in context. Because we're so close to the sun, we're only 150 million kilometers from the sun, and that's the closest star to us. So we can study it intensely, we can see it in great detail. But the sun is only one star. It's as if I were to take one of you out of the audience at random and I were to interview you and conduct psychological tests and medical tests and maybe eventually dissect you. And I would learn a tremendous amount about human beings, but I would get a very narrow viewpoint. I would only learn about one of the two sexes. And so if we only concentrated on the sun, we're not really going to understand our own star as well as we need to. So MOST is designed to look at other stars like the sun out in space and give us a look inside the heart of another star. And on the screen there, you see a number of different colors of stars. There's kind of an orangish yellowish one there. That's one like the sun. Here's a blow-up, a picture of the sun. But it's a picture unlike any that you've probably seen. It's not a picture of the light from the sun. It's a snapshot of the motion of the sun. The sun is a giant ball of gas, and it's literally vibrating like a musical instrument. Yesterday, we were treated to a number of fantastic musical performances that was climaxed by Lara St. John's violin performance. And if you could imagine having a high-speed camera that took a snapshot of the violin strings in vibration, and if you analyze that, you could actually translate that into the sound that those strings were making at the time. And that's, in fact, what we plan to do with the light from stars. That's what we're able to do with the light from the sun. Now, if the technology will indulge me, I have a sound file. You wouldn't be able to, if we could go back to the previous picture, and if we could play the sound file. The vibrations of the sun are beyond the pitch of human hearing. They're only a small fraction of a hertz. And we wouldn't be able to hear them through the vacuum of space anyway. But what we can do is take those vibration frequencies and bring them into the realm of human hearing. And that's what you're listening to right now. It's like the heartbeat of the sun. More like the sleeping breathing of the sun. Now, it doesn't sound like much, but I mean, probably if Moby sampled this, he could make $1 million. So here's another connection. Those of you who are composers out there might find some inspiration in the beating of the many frequencies, the literal harmony of the spheres that we have in the sun and that we're hoping to detect in other stars, because the other stars are too far away. That stellar orchestra is playing so faintly that we can't hear it. We can't see that from the surface of the Earth through the turbulence of the Earth's atmosphere. But the MOST space telescope above that atmosphere, properly designed in the right orbit, will allow us to listen to and interpret the stellar symphony. Thanks. The other thing that MOST will do, again defying expectations for its small size, is to study planets around other stars. And in recent years, astronomers have succeeded in detecting a number of exotic, mysterious alien worlds, not likely to be inhabited. And MOST is going to be able to tell us more about them because they're surprising worlds. And let me just take a moment to sort of put things in context. Here's another picture similar to the one that I showed you before. This is a picture of an interstellar nebula. Now, nebula is just astro jargon for a cloud of gas and dust. The reason we do that, cloud has one syllable, nebula has 3 syllables, so it's a good scientific term. And this is where astronomers believe that stars and planets are being born. And there are many such clouds throughout the galaxy, and in fact, we believe our own solar system formed from just such a cloud. To put it in scale, you're looking across, if we were all sitting in the audience on one side of the cloud, and the photographer, Simon, that we had last night taking the group picture, was there with his camera, stereoscopic or otherwise, and the flash went off, it would take 15 years for the light from the flash to arrive and strike us, and another 15 years for it to be reflected back to the camera. So nobody had better have moved or you're going to ruin the picture. He wanted us to be still for half a second. So these are big clouds, and their composition is 98% hydrogen and helium, and everything else in the periodic table represents only 2%. Tiny fraction of the composition of the visible universe is made up of the stuff that we're made up of. So we really represent rare constituents. And in fact, astronomers infer that the vast majority of matter in the universe isn't even visible to us. We call it dark matter. And so we drop down to even a lower level of significance in terms of the cosmic makeup. But by studying these clouds, we do find some encouraging signs about whether we might eventually find life elsewhere. Because we find that these clouds contain the building blocks of life. They contain organic molecules. They contain water molecules. They contain amino acids. So it's the things that are necessary for life as we understand it to develop. They also contain this last compound. Now, I know we have a Nobel Prize-winning chemist in there, so you're not allowed to answer this question, but anybody know their organic chemistry and can identify that compound? Ethanol, ethyl alcohol. That's my personal favorite organic molecule, as many of you discovered last night. And it turns out that in a cloud like the one that you saw there, there's enough for basically a huge number. We don't even have names for numbers that big. A 1 followed by 28 zeros, fifths of 100%, 200-proof alcohol. And apparently, when this was reported in a press release, NASA radio astronomers discovered this, an American distilling tycoon approached NASA to buy the rights to the Sagittarius B2 star-forming cloud. Here's another connection. And it's unfortunate that NASA didn't have any really financially astute people on there, because they would have sold the rights for whatever he was willing. One of these Texas people would go up and say, it's mine. They should have just sold him the Sagittarius B2 cloud. Because although there's a lot of alcohol there, it's very thinly dispersed. A spaceship with a funnel a kilometer wide, traveling at 10% of the speed of light, would still take a millennium to get enough alcohol to get a decently dry martini. And again, in deference to our sponsors last night, but the point is that the raw materials, the building blocks are out there. And we just need the right environment, the right kind of planet. But the planets that we'll be finding are defying our expectations. One of the themes of this. They're larger than we expected. They're closer to their parent stars than we ever expect. And many of them would be totally uninhabitable. This is just a chart showing the relative positions of some of these planets compared to their stars and scaled to our own solar system, the inner solar system. Some of you can see Mercury, Venus, Earth, and Mars at the top of this chart. And then highlighted here are regions. It's like Goldilocks and the Three Bears. You know, it's just the Earth is in an area that's just right, where the temperature allows liquid water to exist and an atmosphere with enough of a greenhouse effect to keep us at a comfortable temperature. If you get too close to your star, then you get too hot and you get a runaway greenhouse effect like Venus. And it's a hellish environment, the melting temperature of lead on the surface. If you go too far out, you're in the icebox. Water freezes, and again, life as we know it cannot come to be. So there's a very narrow habitable zone. And some of these worlds do appear to fall in that zone, but the worlds themselves would not be habitable. They might have moons around them on which life could exist. Most is going to be able to study some of these worlds and tell us what they're made of. We have no idea what their composition is. We have no idea in detail how they formed, although there are theories. And we're going to have, hopefully, next year after the launch, some of the first direct observational data on some of these worlds. Because we'd like to check whether the idea that astronomers have promoted, mainly thanks to Carl Sagan, for the last few decades, what I like to call the Star Trek universe of a galaxy teeming with life forms. Biologists would consider to be biodiversity. This really isn't biodiversity, by the way, because these are all just like two-legged creatures with different foreheads and ears, but you get the idea. Is that true, or is life rare? Now, astronomers argue that we think life is out there in abundance because of sheer statistics. Our own galaxy, the Milky Way, I apologize, some of the format's been distorted going from one computer to the other, contains about 100 billion stars. And we believe that there's about 100 billion galaxies in the observable universe, thanks to observations by things like the Hubble Space Telescope. And that gives us something like a 1 followed by 22 zeros stars. That's a lot of stars. And it's hard to believe that our star is the only one that has planets that have life, and only intelligent life. Biologists, on the other hand, maybe take another tack. They say, well, what do you need to create life? You need organic molecules. No problem. We've got them everywhere in the galaxy. You need phosphates. Those things exist, probably, in some form or another, combined with organic molecules, using water as a solvent to create proteins and nucleic acids. Then somehow, and in a way that's certainly not clear to me, and I'm just a rocket scientist, you get RNA and DNA. And many biologists would argue, and I think quite justifiably, that the odds of all of these things happening are 1 over a very big number. And if you multiply those two numbers together, maybe you get a small number, maybe 1, maybe a handful. So it's hard to tell. Are there millions of civilizations and habitable worlds out there, or is there 1 or a handful? And these are the kinds of questions that we're trying to answer, and MOST will add its small piece of the puzzle. Another way of looking is to listen, see if we can eavesdrop on the Moses Neimers of the galaxy and elsewhere in the galaxy. They don't even have to be trying to signal us, because if they're using TV and FM transmission, those are leaking through their atmospheres out into space, just as ours are. And so if there were alien radio astronomers on a planet 36 light years from us, they'd just be getting the first episodes of Gilligan's Island. Probably explains why we haven't heard from them. And again, in deference to our sponsor, are you still carrying Gilligan's Island, by the way? I know that I'm going over time, and let me just rush through this. One thing that MOST will do in a second generation, we are now investigating the possibility of using MOST as a cosmic traffic cop to figure out how much junk is out there that might cross the Earth's orbit and eventually hit us in a kind of an Armageddon direct deep impact scenario, and we can't count on Bruce Willis to save us necessarily. Canadian astronomers are at the forefront of this search from the ground. This is a picture of the telescope outside of Victoria, the Dominion Astrophysical Observatory, Herzberg Institute of Astrophysics, and David Balaam at the University of Victoria has used that telescope to find asteroids and track their orbits. And you might not be able to spot the asteroid in this picture, but there it is. The streaks are stars that are not being tracked by the telescope. And this particular asteroid turns out to be a couple of kilometers across. And it won't hit us. We know that. But if it did, it would leave a hole that big, like this one in Ghana, when the Earth was hit by something about that big millions of years ago. And so we hope to use MOST to be able to figure out whether we have to worry about things like this happening. Now, there's a positive side to this, too. I mean, the risk of us being hit by an asteroid for causing global extinction is relatively small. I'm certainly not losing any sleep. I lost a lot more sleep over preparing for this talk than I lost about worrying about asteroids striking us. But look at this enormous chunk in this artist's conception of ice and rock coming, in this case, hitting the Earth. But there are lots of them that come close to the Earth, and MOST will find those. And those are ones that are easy to visit. You don't need a lot of energy. You don't need a really powerful rocket to go to something which is sort of in the same lane as you are in the in the interplanetary highway. And so MOST will identify these, and these things are chock full of gold and platinum and rare earths and elements. It's been estimated that the total value of the surfaces of some of the near-Earth asteroids that we could access might top $100 trillion. And so MOST and Canada might have an opportunity to identify some of these things for asteroid mining, near-Earth asteroid prospecting. And this could be a niche in which Canada leaps in, because you don't need big rockets, you don't need big satellites, and we'll have the tool to find them, and then that might inspire other universities and Canadian industry to build the tools to land on them and prospect them eventually. Well, I appreciate the time you've taken. I believe, do we have Bart Netterfield talking later this morning? So just to set up Bart, who's a fellow astronomer, I'm looking at the building blocks of galaxies in the universe, the stars, just as the atoms are the building blocks of your body. You're going to hear about the bigger picture, the entire universe, and so on. And some of you have seen the cover of Time magazine, and Bart has been a key player in some of this research. So this has sort of set the stage on one level. It's hard to believe that you could go to an even grander, broader canvas, but I've been looking at the pigments, and Bart later is going to show you the broad sweep of an extremely exciting canvas, which kind of echoes IdeaCity, which is one of the broadest and most satisfying intellectual and emotional canvases that I've had a chance to experience. Thank you all.